Hello and welcome, guys, to another session in the Mind Grid. And today we're talking about a continuation part two to our intro to networking um, video. And using myHDL, today we're talking about layer 3 IP parsers and how these work and how we can design them. All right, so as usual, the goals are first, we try to understand what layer 3 is, what does it entail, what are the protocol headers, etc., that we need to parse through. In the previous video, we already saw what layer 2 was, the MAC layer, the Ethernet layer. This time, we're talking about the IP layer and all the intricacies of the IP layer. Then we will try to design an L3 parser to detect layer 4, which is most cases UDP, TCP, GRE. There could be other protocols, but we'll just try to detect today the start of layer 4. Okay, that's the purpose. That's the sole purpose of layer 3 parser. Then we will see how we can simulate and debug this, and using tools like myHDL obviously for simulation and gtkwave for debugging. All right. So that being said, let's move into our handy dandy block diagram. So we already talked about L2 parser. Today we are on the second block, which is the L3 parser. And then we will move on to layer 4 and finally the GRE strip, which is removing the GRE header of the tunneled packet, right? So that's the sequence. And so then moving forward, I guess we'll look at IP layer here real quick. The IP layer, as I'm showing here, there is two different headers. If I may get a pen here. So the layer 4, which is I guess the simpler of the two, is shown here, and it's a smaller header. I think it's 20 bytes. So this is like 4 bytes, 1, 2, 3, 4, 5. Yeah, so it's 20 bytes, and it may have optional headers, and then following is the data. This is called IPv4. You're probably aware of, using IP addresses, which are like 192.168, 1.50 or something. Those are IP addresses. They belong in the IPv4 category. And then the IPv6 is the other protocol, which is slightly different. It's got bigger addresses and more complex options, fields, and so on. So this is our IPv6 header. Overall, they're roughly the same. They have ability to define source and destination addresses, and then they may carry some other routing related information inside them using optional headers, and then what class of traffic they are carrying and some ability to handle flows. So this is kind of what is there in each of these. For example, if you look at this, there is a protocol field here that tells you if there's a TCP, UDP, GRE, etc. following, and you don't see a protocol here because these are usually carried inside the next header field, and so the next header field would be in IPv6 is what is going to say. So that's, I guess this is the next header field, and that's what says. So if there are options headers following this, then this next header will basically be pointing that what is following is some sort of a header that is following the options headers, or it is TCP UDP, and then this would chain into the next one, and so on and so forth. So they would just keep chaining into each other. And so that's the IP layer in general. If you have questions, leave me in the comments, but it's pretty straightforward. All right, so next up is now we start parsing, right? So before we go into the code, I just want to give you a couple of tips and tricks. Now, in the previous video, we saw that obviously the layer 2 could have been in the previous clock cycle. Now, each clock cycle in our case is 32 bytes. So 32 bytes here, 32 bytes here, and so on. Every clock cycle is 32 bytes, right? Going on and on, however big the packet is. Now, this first packet had header metadata here, and then the packet started halfway through. And so then there was a MAC header here. It could have VLANs in here, and then L2 may spill over here in the next clock cycle, or it may end here, right? So it's possible that your IP layer starts right there, layer 3 starts right there. So there's multiple possibilities, and accordingly, your L2 parser and L3 parser have to be sophisticated enough to do all this. Now, in this case, I'm showing you if the IP starts, let's say, somewhere in the middle of this cycle, and this can move, this starting point can move, this is quite complicated to parse in hardware or an FPGA or an ASIC, because you have to basically designed for every possible alignment. Like if this protocol, layer 2 protocol, had two VLANs, or if it had some other options like MPLS or something, this IP layer will keep moving, and that means you have to basically account for every possible alignment, and that becomes very complex. So the trick here is going to be that we will move this alignment so that it aligns to the top. And so when this start of the IP header is indicated by the L2 parser, we will look at it, we'll recognize that this is the start. It could be here or here, and we'll move it to the top, which means that we have to bring in data from the following clock cycle to make 32 bytes here in this clock cycle, right? So we'll have to make 32 bytes somehow, because that's what we need to process a single clock cycle. Unless there's end of frame, in which case, you don't have 32 bytes, you have less than 32 bytes. So this is kind of a trick that we must align data to the top of the word, and that simplifies the parsing for our L3 parser. Now this trick is ubiquitous. You will see this trick being applied to every parser that I write, because this trick simplifies all the alignments. Now imagine trying to close timing at very high speeds. If you are doing that, your logic must be very, very streamlined. And this is one of the tricks that will help you do that streamline. All right, so next up, we're just showing you the usual, the timing diagram. So you have data. Now each data here is 32 bytes, right? So these are just multiple clocks showing a packet, but each is 32. So 32, 64, 96, so on, so on. It's basically just filling up in 32 bytes chunks. This is the data. And then there's start of frame. This is where it starts. And you know that the first clock is half of metadata and 16 bytes of data of the MAC, Ethernet, whatnot. It starts there. And then this is the end of frame. And at end of frame, you also need this tag to say exactly out of the 32 where the end of frame aligns. So that you need here. Now, we have been given L3 SOF and L3 tag by the L2 parser. So all this is a given, right? All this is a given. And then what we are detecting is where the L4 starts. So if L3 were to start here, or if L3 were to start here, wherever, if either starts in the very first clock or the second clock or even the third clock, let's say, it doesn't matter, then you have to basically parse where L4 starts and produce a tag for it, right? Because the L4 may start anywhere in the 32 byte lane alignment. So you have to figure out where exactly it starts. So that's the purpose of this, right? Hopefully that's clear. All right, so here's a view of the state machine. Now state machine, this one looks a bit complicated, but it's really not that complicated. So let's take a different color and let's look at the idle state. So this is where kind of we start, right? And from this will basically start when you get the start of frame, right? That start of frame is where, you will start doing work. And that start of frame is not an L2 start of frame, it's an L3 start of frame. Once you see the L3 start of frame, you will start your work, and you'll basically see either the L4, which is TCP UDP GRE, lies in the same clock as the idle. So in which case you detect the L4, right? Because it's there right away. As soon as you get the SOF, you've also got the L4 in that same clock. And if that's the case, you just go to EOF and wait for the end of the packet, right? So that's the first transition. The second one is that if it's IPv6 and it doesn't fit, so IP has started here, the SOF was the IP SOF, and if it doesn't fit in the clock cycle, you may have to go in a second clock cycle to finish all the IPv6 headers, because IPv6 is significantly bigger. So it may go to the next clock cycle, right? And then IPv6 layer. And then another transition is if you haven't received SOF, so you just keep looping around. So this arc here is if you don't have anything, then you keep looping in this idle state, right? And then you have this one where if you have L4 after this clock, so you've got L3, but L3 is too long and it's not IPv6, and somehow L3 has some other things, so it goes into this data state, right? So it'll go into the data state and it'll look for the L4 header in that following subsequent clock cycle. So it'll just keep going. If it's any of these options, then we'll basically have detected how to handle the L3 and where the L4 lies and handle it. Now, once you get the EOF, obviously if the end of packet L2 EOF is seen where the packet ends, you go back to idle. And same here, if you see from data, either, if L4 is seen in this clock cycle, which if you see, you are waiting for L4. As soon as you get L4, you wait for EOF. But if you have found L4 and you found L2 EOF at the same time, then you just go back to idle because you're done, right? And you'll wait for the next packet. So essentially, this is the state machine, right? And so I think this is all that I have in the slides. Now let's dive into the code here. So as usual, this is using myHDL, nothing special. There's some math functions involved, but this is the definition, right? So in the input definitions and output definitions, you will see this parser L3 256, and I call it 256 because it's 32 bytes or 256 bits. That's basically the dimension of the data bus. And so this is reset and clock. It has L2 interface, and from the L2 parser, the L3 signaling, which is L3 SOF and L3 tag, then L3 extract. So that might have some other metadata that might say what is, protocol, etc., coming for the L3 that was extracted in the L2 parser. Then you have the output interface, and these are all output interface. That's why I call it L3, because L2 was all the input interface and L3 is all the output interface. This L3 extract is actually belonging here. So, or actually it may belong here as well. L3 L2 interface, L3 L3 interface, L3 extension interface, and L3 L4 interface. This is kind of the next in line, but sometimes there is also L3 extensions. There is extension parsers that may be required. So I am supporting some of the L3 extensions, very complex parsers which require L3 extensions, but I will show you how it's done. So then moving on, as I've showed you in the diagram, there is the states, data, idle, EOF, IPv6 and idle. And then you have obviously the definition of the interfaces. Now these interfaces, like I've shown you before, they come from the package file, and it's pretty straightforward. Let me show you that. So package file will basically define each of these interfaces. So like L3 interface is SOF and EOF and tag, out of which, L3 interface will probably end up just using SOF and tag because EOF really has no meaning. We'll just use L2 interface as the end of frame. So we really have these two signals that are used. And likewise, if you look at L3 extract, maybe you can see what it contains. L3 extract is right here. Sorry, L3 extract is not there. Let's see where L3 extract is. Okay, there's the L3 extract. It has L3 level information, so it has all the data in the L3 layer. Various fields can be extracted by the L3 parser, so they're all there. So the package basically is defined different classes that we'll use as helper classes when we do our L3 256 parser. All right, so some other internal signals that are defined here, you can go through them, but let me just go over the big pieces. So and then this is basically you have some pipelining going on because we need 2 clock cycle delayed version of the data and SOF UF. So we delay them by 2 clock cycles. And then once we get that, we align, because like I showed you in the tips and tricks section, we need to align the data to the top, right? And so the alignment is a little bit complicated because we use the tag, and using the tag, wherever the L3 SOF starts, its tag is where you have data, and that's where the L3 data starts. So this is to shift that data by that. And so that's what we have done, is we have basically taken that data, shifted it up, and taken the next clock cycle data and shifted it into the empty space, and therefore you have got the aligned data. And that'll happen every clock cycle. For this packet, it'll keep happening for every single clock cycle. You would shift by this certain barrel shifter that'll keep shifting till the packet ends. So that's the tips and tricks section that I showed you earlier. Now is the state machine. So now you get into the state machine. So when you have idle, in the idle state, if you get the start of frame, right? So I think that somewhere you will wait for the start of frame. So here, so aligned SOF. Now, what I mean by align is that once I get the SOF, I push it to the top of the data is aligned to the top of the byte or the word, and then the SOF is that SOF. So whenever I get the SOF, I basically assume that there's most of the L3 extract data will be present there. And if I have, all the data received, then I can decide to go, if there is, a certain amount of data received, then I can decide if I go to EOF or I go to data. Those are the assumptions I've already described to you in the state machine. And if it's version 6, then I extract all the data. And then if I have to go, I would basically, if IPv6 is there, I will go to IPv6, the second stage, because all the data has not been received here in a single clock. Because in a single clock, imagine you only have 32 bytes, but the IPv6 is at least 40 bytes. So you know that you have to jump in another clock cycle. IPv4, not so much, because it only has 20 bytes in general, so you might fit everything in the same single clock cycle. So that's why they're slightly different. And so now if you get into IPv6 2 state, then you have, if it was IPv6, but you see that the next header is either TCP or UDP, then you do certain things that you can figure out the SOF and tag, which is the main purpose of this parser, is to extract SOF and tag. And then if the next header is 0 or 43 or whatever, so there's some extension headers that are supported, then I will put out extension header SOF and tag, which will not say that this is layer 4 coming out, but it'll say extension headers coming out, right? So there'll be an extension header parser after this. Now in the data state, the same thing happens. If you're basically waiting for the layer 4 to start, right? So either you will see the layer 4 start, or you'll keep waiting for the layer 4 to start. So here, you're basically just going through it, and as you finish 32 bytes, you go to EOF, right? So that's what it is. And then if you go past this, now if you're seeing an EOF, then you go back to idle, right? So if you see an EOF, you go back to idle. Otherwise, you're basically just collecting data here, because you have already seen the L4, and you already know that which L4 it is, because by the time you get to the data, you know that which version of the protocol is being used, and you're just going to finish off till you get the end of file, end of a frame, or you will go, if you see the EOF, then you go to idle. So that's pretty much all that happens. If it doesn't find the EOF, it just keeps cycling here, and actually that is all that happens in the data state. And then you have the EOF state, and the EOF state, if you come here, then you just go to idle whenever the L2 EOF comes, and so that is that. Now, in myHDL, you always need this return, and the return always needs to have all the blocks, right? So if you define multiple blocks, so for example, here, you see that this block is called logic. This is the main state machine, it's called logic. And these are called pipeline or pipe input. So you have to return everything from your main function. Return pipe input, pipeline, logic, right? So that's important. Now that we have seen all the code, let's maybe try to run this. So the way you run this is I just compile it using Python. And I call it MPython because I have aliased, because this is a special version of Python that I'm using here. I'm using WSL in Windows, which is a Linux port inside Windows. And so I had to alias Python, so that's why it's called MPython. Now I have run this, and the whole simulation has finished. Now I have to say gtkwave test.vcd, and that'll start the waveform viewer. Let's see if I can find my waveform viewer, expand it, and then I'm just going to load my save file, which was something I'd already done before. And so here you can see this is the output interface, And so the data is coming in, and you can see that it's extracted the destination source address for IPv4, extracted the version, which is IPv4, right? And 4 is L3's version was 4, right? So it has extracted protocol, and let's see what protocol it is. Data format is decimal. Okay, so 47 I think is GRE. So that's what is extracted. The next protocol, layer 4 protocol, is GRE. And you can see that it's extracted the L4 SOF and L4 tag, right? So those are the two things that it has successfully extracted. And then that was the main purpose, right? Is to extract and indicate where layer 4 lies. Now, if there is also extension headers, then you have to go through extension headers as well. In this case, there are no extension headers. And I'll show you maybe in a follow-on video how to deal with extension headers, because that'll take its own time. An extension header parser is almost like a layer 3 parser. Because it's quite complex for an FPGA designer. Right? For software designers, it's fairly simple because it's just like a linked list sort of headers. But for an FPGA designer that's operating in like multiple bits data paths, it's not that straightforward to close timing once you design something that's quite complicated and variable length. I mean, if these headers could be like, 16 bytes or 24 bytes or 32 bytes, and then multiples of them a single clock cycle, it may get pretty complicated to handle. Leave me some feedback if you already have been designing FPGAs in wide data buses, and what is your view. But my view is that you design it in simplest possible way so that it's the simplest alignment, and that's the trick I've already showed you, simplest alignment, and then you do just one complex header parser in one, right? Don't try to do multiple different header parsing inside a single clock cycle. That's going to get very complicated and probably not going to meet timing. So yeah, if you have experience in this domain, have been doing this, leave me some feedback and tell me how you do it, and if you agree with my ideas and suggestions here. So now that we have done the L3 parser, we have showed you how this can be simulated, and you can obviously go through this diagram and see if there's something wrong. You can debug it, and you can change it, and then come back here, simulate it again. The whole experience is kind of like Verilog or System Verilog, where you make some changes and you simulate, you see the waveforms. It's pretty much the same. It's almost like out of the box experience in myHDL is the same as Verilog, System Verilog, using Model Sim or Cadence or whatever you're using, even like Questa or whatever Vivado, whatever you're using. It's very similar because most of the things are the same. Now there's some tricky small nuances that you will probably have to deal with because the code is written differently in Python, obviously, and it's slightly nuanced. But once you get over the nuances and you find your rhythm, then it's kind of very similar. So I will end it at this point, guys. Hopefully you liked the video. If you have any questions, leave me comments. And I am going to bring in the next video shortly where we look at the parser extensions. Like I said, L3 parser extensions, or like IPv6 header options, or even IPv4 header options. If there are multiple options, they may get very complicated. So my thought is that our parser will support only certain amount of options and not like infinite number of options. And this is maybe usually okay in hardware design. So you may be able to tag like 4 or 5 or 6 different extension header parsers, which is what the approach that we will take. Here is maybe I'll show you 2 different parsers, extension parsers, and how they're done in the next video. So if you want to watch that, stay tuned to my channel and hit the subscribe button and hit the like button if you enjoyed this video, and I'll catch you in another video. Until then, take care and bye-bye.